Good morning to one and all. Just I am sharing my screen. Today we have to start with the analytical. We already started the unit 2, which is nothing but that particular your gas chromatography. Just I am sharing the slide. Is it visible? Screen is visible?
Yes, sir.
Okay. The second unit method of separation gas chromatography is there. In that, you see the introduction, principle, theory, think so. Then instrumentation, block diagram, and the component types of the column, stationary phases in GSC and GLC, detectors, TCD, FID, ECD. Quality, quantitative analysis that we have to see comparison between the GSC and GLC. These both are the gas chromatography technique. Ion exchange chromatography, in that we have to talk their principle, then types of the ion exchanger, their properties, means properties of the resin, then ion exchange equilibria, how it happens, actually how it is equilibrated and how it gets separated, then selectivity coefficient, that all parameters. Talk about the ion exchange capacity and their determination for the cation exchanger and anion exchanger, then the application with reference to the preparation of the demineralized water and the separation of the amino acid. This is the your syllabus for the unit 2. As already we have discussed about the gas chromatography. Gas chromatography, you know, that is a separation technique, okay, in which the mixture is get separated into its components using the two phases. Two phases are required, that already I discussed with you. One is the SP and another is the MP. SP is nothing but the stationary phase and MP is nothing but the that your mobile phase. Then the classifications are there. This is the introductory part. Okay, in the gas chromatography, you have to remember that there is the mobile phase gas, right? And stationary phase may be the solid and the liquid. Okay, that's why there are the two techniques. One is the GSC and another one is the GLC. GSC is the adsorption technique, adsorption chromatography. It is a type of the adsorption chromatography, whereas the GLC is the type of the partition chromatography. What happens in that particular techniques? One, the separation of the component occurs with the help by the, you can say, by the adsorption technique, and in the GLC the separation of the components occur by the partition. Their principle you can see here, same thing is there, whatever I just talked. Okay, this particular separation is based on the partition. We are talking about the GLC. First of all, mobile phase is a gas, stationary phase is a liquid. Components to be separated will be converted to the vapor and mixed with the mobile phase. Component more soluble in the stationary phase travels slower, and component less soluble in the stationary phase travel faster. No two components have same partition coefficient for the fixed combination of the that particular your the stationary phase and mobile phase and other condition. Okay, then we will see just this particular part. Just I'm playing this video.
Chromatographic separations. What is chromatography? Chromatography is a powerful separation method that is usually composed of mobile phase and a stationary phase.
It is audible, visible? Please anybody
Yes, sir.
unmute yours. Okay, okay.
Introduction to chromatographic separations. What is chromatography? Chromatography is a powerful separation method that is usually composed of mobile phase and a stationary phase. This method is used to separate and identify the components of complex mixtures. Works by allowing the molecules present in the mixture to distribute themselves between a stationary and a mobile phase to varying degrees. Those components that are strongly retained by the stationary phase move slowly with the flow of mobile phase. In contrast, components that are weakly held by the stationary phase travel rapidly. As a consequence of these differences in mobility, sample components separate into discrete bands that can be analyzed qualitatively and or quantitatively. Classification of chromatographic methods can be categorized based on the followings. 1. Based on physical means. The way stationary and mobile phase are brought into contact. 2. Based on the types of mobile phase, either gas, liquid or supercritical fluid. 3. Based on the kinds of equilibria involved in the solute transfer between the phases. Interaction of analyte between stationary and mobile phases. Classification of chromatographic methods. Column chromatography. Stationary phase is supported on a flat plate or in the interstices of a paper. Mobile phase moves through capillary action or gravity. For example, thin layer chromatography, TLC. Paper chromatography, PC. Stationary phases is held in narrow tube. Mobile phase moves by pressure or gravity. For example, gas chromatography, GC. Supercritical fluid chromatography, SFC. Based upon physical means. Column chromatography can be further differentiated based on the types of mobile phases and the kinds of equilibria involved in solute transfer between the phases. Mobile phase. I. Gas. Gas chromatography. 3. Supercritical fluid. Supercritical fluid chromatography. 2. Liquid. Liquid chromatography. Types of chromatography on the basis of interaction of the analyte with stationary phase. Adsorption, for polar non-ionic compounds. Ion exchange, for ionic bonded phase has positive charge. Cation, analyte is cation, bonded phase has negative charge. Partition, based on the relative solubility of analyte in mobile and stationary phases. Normal, stationary phase polar, the mobile phase nonpolar. Reverse, stationary phase nonpolar, the mobile phase polar. Size-exclusion, stationary phase is a porous matrix sieving. Classification of chromatographic methods. Chromatography. Partition. Adsorption. Ion exchange. Size-exclusion. Liquid-liquid. Liquid-solid. 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 Gas-liquid. Gas-solid. Partition chromatography. Partition chromatography. Accomplished by selective and continuous transfer of the components of the mixture back and forth between a liquid stationary phase and a liquid mobile phase as the mobile phase liquid passes through the stationary phase liquid. Stationary phase, liquid. Mobile phase, liquid or gas. For example, stationary phase, polar. Partitioning. Distribution, by dissolving, of the components between two immiscible phases. Relative solubilities of the components in the mobile and stationary phase. For example, stationary phase, polar. Polar components will retain longer than the non-polar components. Non-polar components will move quickly through stationary phase and will elute first before the polar components, and vice versa. Partition chromatography. The stationary phase actually consists of a thin film adsorbed, stuck, on or chemically bonded to the surface of a finely divided solid particles. Partition chromatography. If the mobile phase is gas, the volatility, vapor pressure, and solubility in stationary phase plays an important role. Adsorption chromatography. Adsorption, affinity, chromatography. Components of the mixture selectively adsorb, stick, on the surface of a finely divided solid stationary phase. As mobile phase, gas/liquid, carries the mixture through the stationary phase, the components of the mixture stick to the surface of it with varying degrees of strength and thus separate. Stationary phase, solid. Mobile phase, gas or liquid. Ion exchange chromatography. Bonding sites on their surfaces which selectively exchange ions with certain mobile phase compositions as the mobile phase penetrates through it. Ion exchange chromatography. Ions that bond to the charged site on the resin bead are separated from ions that do not. Repeated changing of the mobile phase composition. The usual procedure is to initially use a mobile phase with all the ions in the mixture bond and then to change the mobile phase in a stepwise chromatography. Adsorption. Chromatography. A liquid carries the mixture through the stationary, thus separate. Stationary phase, solid. Mobile phase, gas or liquid. Ion exchange chromatography. Ion exchange chromatography. Method for separating mixture of ions. Sample, aqueous solution of inorganic ions, organic ions. Stationary phase, small polymer resin beads usually packed in a glass tube. These beads have ionic bonding sites on their surfaces which selectively exchange ions with certain mobile phase compositions as the mobile phase penetrates through it. Ion exchange chromatography. Ions that bond to the charged site on the resin bead are separated from ions that do not. Repeated changing of the mobile phase composition. The usual procedure is to use a mobile phase with all the ions in the mixture bond and then to change the mobile phase in a stepwise fashion so that one kind of ion at a time is removed. Done until complete separation achieved. Size-exclusion chromatography. Size-exclusion chromatography. Also called gel permeation chromatography. Technique for separating dissolved species on the basis of their size. Stationary phase, porous polymer resin particles, molecular sieves. The components to be separated enter the pores of these particles and are slowed from progressing through this stationary phase. Size-exclusion chromatography. Separation depends on the sizes of the pores relative to the sizes of the molecules to be separated. Small particles are retarded to a greater extent than large particles, some of which may not enter the pores at all, and separation occurs. Terminologies in chromatography. Terminologies in chromatography. Elution, a process in which in a column or on the surface of a flat plate. Terminologies in chromatography. Elution, a process in which species are washed through a chromatographic column by addition of fresh solvent. Mobile phase is one that moves over or through an immobilized phase that is fixed in place in a column or on the surface of a flat plate. Stationary phase, a solid or liquid that is fixed in place. A mobile phase then passes over or through the stationary phase. Retention time is the time interval BTW its injection onto a column and the appearance of its peak at the other end of the column. Migration rates of solutes. Distribution constant, K. Retention time, TR. Capacity factor, K. Selectivity factor. Distribution constant, K. In chromatography, the distribution equilibrium of analytes between the mobile and stationary phases can often be described quite simple. Let's say we have analyte A. The distribution equilibrium is written as and mobile or stationary. Therefore, the equilibrium constant K is called distribution constant and is defined as K equals C molar concentration. Stationary. Mobile. K is also called partition coefficient or partition ratio. Retention time, PR. Time required for the sample to travel from the injection part through the column to the detector. A typical chromatogram for a two-component mixture. The small peak on the left represents a species that is not retained on the column and so reaches the detector almost immediately after elution is started. Trademark, time taken for the unretained species to reach the detector. Sometimes called dead time. Rate of migration of the unretained species is same as the average rate of motion of mobile phase molecules. So, trademark can be expressed as the time required for an average molecule of the mobile phase to pass through the column. Retention factor. CHR is greater than 30, separation is slow. When CHR is 2 to 10, separation is optimum. Selectivity factor is defined as equals KB CHR KB. A measure of the relative migration rates of species A and B with a stationary phase material in chromatography. KB. CHR. Distribution constants. KB. CHR. Capacity factors. TRB. Trademark TRA. Trademark. Retention times. TR. Trademark TRB. Trademark TRA. Trademark K == response TR trademark 136. Retention time, min. TR, trademark TRB, trademark TRA, trademark. K equals. Column efficiency. Two related terms widely used as quantitative measures of chromatographic column efficiency. I, plate height, H. 2. Number of theoretical plates, N. Efficient column has small plate height. The relationship between H and N is N equals. The efficiency of chromatographic columns increases as the number of plates becomes greater and plate height becomes smaller. Column length. L. H. Plate height. Number of theoretical plates. Efficient column has small plate height. Experimentally, H and N can be approximated from the width of the base of the chromatographic peak. The equation 2 TR W N equals 16. N can be calculated using TR and W. To obtain H, the length of the column must be known. Another method for approximating N is to determine W half, the width of the peak at half its maximum height. N equals 5.54 TR2. W half, resolution, Rs. A measure of the separation of two chromatographic peaks. Baseline resolution is achieved when Rs equals 1.5. Rs equals 2 TRB, TRA, Y plus WB. Y plus WB. Effective capacity factor and selectivity factor on resolution. Relationship BTW, the resolution of a column, and the capacity factor K, selectivity factor, and the number of plates N is given by this equation. Rs equals N, 1 K, for 1 plus K. Simplified, Rs equals N, effect resolution on retention time. Relationship BTW, the resolution of a column and retention time. 2. TR equals 16 Rs2H, 1 plus K3. U, 1, K2. Simplified, TR equals 2 Rs. Peak widths, at base, for E and B were 1.11 and 1.21 minutes respectively. Example. Length of column, 30 centimeters. Peak widths, at base, for E and B were 1.11 and 1.21 minutes respectively. Calculate. I, column resolution, Rs. 2. The average number of plates, N. 3. The plate height, H. 4. Length of column to achieve 1 rupee and 50 paise. 17.63 minutes. Response. TR. 16.40 minutes. TR 1.30 minutes. Trademark 1, 3, 6. Retention time, min. Hours equals 217. 63 minutes. 16. 40 minutes. 1. 11 minutes plus 1. 21 minutes equals 1. Hours equals 217.63 minutes to 16.40 minutes. 1.11 minutes plus 1.21 minutes equals 1.062. N equals 16. 16.40 minimum 1.11 minutes equals 3.49 by 103. Hours equals 2 TRB. TRA. Y plus WB. 2. TR. N equals 16. 2. N equals 16. 17.63 minutes. 1.21 minutes. H equals L. N equals 30 centimeters. 3.44 by 103 equals 8.7 by 10 to 3 centimeters. Rs 1 N1. Rs 2 N2. Therefore, cal equals 3.44 by 103 equals 1.06 equals 3.44 by 103. 1.5 N2. N2 equals 6.9 by 103. L equals NXH equals 6.9 by 103 by 8.7 by 10 to 3 equals 60 centimeters. Band broadening reflects a loss of column efficiency. The slower the rate of mass transfer processes occurring while a solute migrates through a column, the broader the band at the column exit. Some of the variables that affect transfer rates are controllable and can be exploited to improve separations. Table 26.2 lists the variables that influence the column efficiency. Their effect on column efficiency, as measured by the plate height, will be described in the following slides. Variables affecting column efficiency. Variables affecting column efficiency. Mobile phase flow rate. Particle size. Diameter of column. Film thickness. Effect of mobile phase flow rate on plate height. From both the plots for LC and GC, we can see that both show a minimum in H at low linear flow rates. Effect of particle size on plate height. Refer to Figure 2611, page 773. The numbers to the right is the particle diameters. The smaller the particle size, the more uniform the column packing, then the more tolerant to the change in mobile phase velocity. Effective diameter of the column on plate height. For packed column, the most important variables that affect column efficiency is the diameter of the particles that making up the packing. While for open tubular column, the diameter of the column itself is an important variable. Refer to Table 26-3. The mobile phase mass transfer coefficient SEM is known to be inversely proportional to the diffusion coefficient of the analyte in the mobile phase dm. SEM is proportional to the square of the particle diameter of the packing material, d1p, packed column. SEM is proportional to the square of the column diameter, d2p, open tubular column. As a conclusion, the bigger the column diameter, the smaller the diffusion coefficient dm. Therefore, we can say that increase in column diameter will increase the plate height. Effective film thickness on plate height. Square of the column diameter, d2p, open tubular column. As a conclusion, the bigger the column diameter, the smaller the diffusion coefficient dm. Therefore, we can say that increase in column diameter will increase the plate height. Effective film thickness on plate height. When stationary phase is an immobilized liquid, the mass transfer coefficient C is directly proportional to the square of the thickness of the film on the support particles d1L and inversely proportional to the diffusion coefficient Ds of the solute in the film. With thick films and smaller diffusion coefficient, analyte molecule travel slower. As a result, slower rate of mass transfer and an increase in plate height. Application of chromatography. Qualitative analysis. Quantitative analysis. Qualitative analysis based on retention time. Provided the sample produced the peak at the same retention time as a standard under identical conditions. Quantitative analysis. Analysis based on peak height. The height of chromatographic peak is obtained by connecting the baselines on either side of the peak by a straight line and measuring the perpendicular distance from this line to the peak. Analysis based on peak area. Peak areas are usually the preferred method of quantitation since peak areas are independent of broadening effects. Most modern chromatographic instruments are equipped with computer or digital electronic integrator that permit precise estimation of peak areas. Calibration method, also known as external method, involve preparation of series of standard solutions that approximate the composition of the unknown. The peak heights or areas are plotted as a function of concentration. The concentration of the components to be analyzed is determined by comparing the responses peaks obtained with the standard solutions. Internal standard method. Equal amounts of an internal standard substance is introduced into each standard ensample. The internal standard should not react with the substance to be examined. It must be stable and must not contain impurities with a retention time similar to that of the substance to be examined. The concentration of the substance to be examined is determined by comparing the ratio of the peak areas, or heights, due to the internal standard in the test solution with the ratio of the peak areas, or heights, due to the substance to be examined and the internal standard in the standard solution. Area normalization method. In the normalization method, the areas of all eluted peaks, the percentage content of one or more components of the substance to be examined is calculated by determining the area of the peaks as a percentage of the total area of all the peaks, excluding those due to solvents or any added reagents and those below the disregard limit. Tailing and fronting of chromatographic peaks. A common cause of tailing and fronting is a distribution constant that varies with concentration. Fronting also arises when the amount of sample introduced onto a column is too large. Types of column. There are two types of column: packed column, capillary column. Packed column. Modern packed columns are fabricated from glass or metal tubing. These tubes are densely packed with uniform, finely divided packing material or solid support, coated with a thin layer, 0.05 to 1 micrometer, of the stationary liquid phase. The tubes are usually formed as coils. Capillary column. Capillary column, also known as open tubular column, early wall-coated open tubular, WCOT, column were constructed of stainless steel, aluminium, copper or plastic. Later, they are made from glass. The most widely used capillary columns are fused silica wall-coated, FSWC, open tubular columns. Column constructed of fused silica tubing. Polyamide coating gives it strength. Outer layer. This resulting columns are quite flexible and can be bent into coils. These capillaries have much thinner walls compared to glass columns. Liquid stationary phase is coated or chemically bonded. Most applications utilize FSWC open tubular column, replacing cod glass column.
ओके पूरा ये जो प्रेजेंटेशन था 20-23 मिनट का, इसमें पूरा क्रोमेटोग्राफी अच्छे से एक्सप्लेन किया है जो कि आपके सिलेबस में है. Okay, as it is, all the part is there. You can see again recorded video. I will share with you, and you can see that. Okay, you can left here. We can join at the physical.